In this video tutorial, I'm going to be digging down to find out exactly what determines the actual position of equilibrium for a reaction. Because we know if we've got a spontaneous reaction, so I'm thinking of something like magnesium, drop a piece into hydrochloric acid, magnesium chloride, lots of bubbles, we make hydrogen gas. This is an example of a spontaneous reaction, and then with a spontaneous reaction that's happening either because we've got an increase in the total entropy of the universe, and we can see in this reaction that producing a gas and a solution from a solid and a solution certainly would give us an increase in entropy of the system, or we can define a spontaneous reaction in terms of a decrease in Gibbs energy. But how can we explain a reaction that's reversible? I'm thinking of something like, let's go with 2NO2 which comes to an equilibrium mixture with N2O4. In our equilibrium mixture, we've got significant amounts of both the reactant and the product. And that happens whether we start from a position of pure NO2 or pure N2O4. Well, let's plot this scenario on this very simple graph here. We have got Gibbs energy up the side. At this point here, we have got pure NO2, pure reactant, and at this point here, we've got pure N2O4, or product. And clearly, as we can see, Gibbs energy must decrease. It must be negative as we move from either pure NO2 or pure N2O4 towards our equilibrium position. And our equilibrium position is the lowest point of the curve, which looks to be about here. So we're going to make that our equilibrium position. And we can see that we have got decreasing Gibbs energy if we move from a position of pure product to our equilibrium position, and equally we've got a decrease in Gibbs energy as we move from pure reactant to our equilibrium position. But the thing is, our equilibrium position has a lower Gibbs energy than either pure reactant or pure product. Equally, we can see that if we moved from our position of equilibrium, either to a point where our reaction was complete, in the classical sense, or back to a point where we just had our products, both of those cases involve an increase in Gibbs energy, which means that reaction is not spontaneous, it's not permitted. So hence we stay at our equilibrium position where our mixture has a lower Gibbs energy than either pure products or reactants. So what influences the actual position of equilibrium? Well, as is often the case, the answer is our old friend entropy. Imagine starting with pure NO2 in our reaction vessel, and then even a really small amount of that converts to N2O4. So here's my N2O4. We'll make those nice and green. I hope we can see the difference between the two there. The fact that we've now got two different molecules in our reaction vessel leads us to a big increase in entropy, because there's going to be a big increase in the amount of disorder or randomness or chaos within our system. And since change in Gibbs energy is equal to the overall change in enthalpy minus T delta S, S standing for entropy, T for temperature of course. So we can see here an increase in entropy is going to lead to a decrease in Gibbs energy because of this negative term. In fact, it turns out that the position of equilibrium actually depends only on the difference between the molar Gibbs energy of the pure reactants and the pure products. So going back to our first example, if I take my pure NO2 and my pure N2O4, this value here would be the molar Gibbs energy of N2O4, and this here would be the molar Gibbs energy of pure NO2. And as we move from pure NO2 towards our equilibrium mixture, all that is changing is the percentage of N2O4 in our mixture. Looking at a different system, this is for the reaction of, I'm going to go with A going to B, lacking imagination today as you can see clearly. Once again, Gibbs energy. We've got A and B, reactant and product. As we move from A to B, the percentage of B in our mixture is increasing. This here is the Gibbs molar energy for substance B and for substance A. And in this case, since B has a lower molar Gibbs energy than A, our position of equilibrium lies more strongly to the right. In comparison with NO2 and N2O4, NO2 had a lower molar Gibbs energy than N2O4, hence the position of equilibrium lay further to the left. There was more or a higher concentration of NO2 in our equilibrium mixture than there was of N2O4. So this is our minimum, can't spell minimum today, our minimum value of G, our Gibbs energy. But it's also something else, because at equilibrium, the concentration of A and B that's present in our equilibrium mixture is going to be described by our equilibrium constant K. And it's products over reactants, so it's the concentration of substance B over the concentration of substance A at equilibrium. So this minimum value of G is also our value for K, the equilibrium constant. Now we can pull all this together with a little bit of maths and a sprinkle of magic. We can go on to say that the difference in molar Gibbs energy between our product, B in this case, and our reactant, A, which is more commonly known as delta G, is equal to minus RT ln K. So K is our equilibrium constant, R is our trusty gas constant, T is the temperature in Kelvin. As we can see from this graph here, if the Gibbs molar entropy of B is less than that of A, then the position of equilibrium lies to the right. In other words, if we go back to our little equation, position of equilibrium lies to the right, which implies that there is a greater concentration of B in our reaction mixture at equilibrium, which means that a big number divided by a little number, if we were, well, let's put our equation for equilibrium constant back in, K equals the concentration of B over A. If position of equilibrium lies to the right, we've got a greater concentration of B. So K is going to be greater than 1. In terms of this equation here, that tells me that delta G is going to be negative and ln K is going to be positive. That's the scenario where we have got, let me just do a quick sketch, A and B, and A has a greater Gibbs molar entropy than B, and so position of equilibrium lies to the right. The other scenario, of course, is where we have got, a bit like with NO2 and N2O4, so let's use that, N2O4, where B has a greater molar Gibbs energy than A, products more than reactants, in which case, let me just change colour. We're going to have a greater concentration of A in our reaction mixture. We see that because position of equilibrium lies to the left in our reaction mixture, which tells me that K is going to be less than 1, i.e. it's going to be a fraction. If you have ln fraction, our ln K is going to be negative, and delta G is positive. And it's positive, of course, because we have got our molar Gibbs energy of B being greater than A. If we go back to our equation, if B is greater than A, then one take away the other, a positive value. However, the main takeaway from this video tutorial is that reaction mixtures that move to an equilibrium position do so because as we can see here, the minimum value of Gibbs energy is lower for the reaction mixture at equilibrium than it is for either the reaction going to completion, where we have just products present, or going back to a point where we just have reactants present. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.